I'm Bill Shipman, CTO and co-founder of Polaris Quantum Biotech. Presenting with me this morning is our principal software engineer, Mr. Maurice Benson. So today I want to tell you a little bit about Polaris, a little bit about drug discovery. Maurice is then going to take the mic and talk about how we're implementing our processes on D-Wave's quantum annealer. And finally, I'm going to take the mic back and talk a little bit about pair of case studies. So with that, Polaris was founded in early 2020 in Durham, North Carolina. Since that time, we've worked on 20 drug discovery projects. And late last year, we launched Quad, our software as a service SaaS offering for large and mid-sized biotechs. So with that, oops, got a slide ahead of myself. So let's talk a little bit about drug discovery and drug design. As I think we're all aware from media, it's a long and expensive process. It's long because you're having to do wetware synthesis. You're actually having to test physical compounds and analyze those results. It's expensive, again, because we're dealing with wetware physical processes, large CapEx expenses for the actual infrastructure required to do the testing. And one point that is not well captured in the media narrative and by the broader public is the limitations of the current process. Essentially, you're dealing with the chemistry you have on your benchtop, what you have in your cabinet, or what you can buy out of a catalog. So the chemical space you're actually exploring in drug discovery is incredibly narrow. So to dive a little bit deeper into the current industry process, which takes on average 3 years and $4 million, it's a set of sequential optimizations. So we'll start with the binding of a small molecule to a protein. This is all for small molecule drug discovery, not biologics, not immunotherapy. We're only in the space of small molecules. So you'll start with optimizing a binding. You're going to spend anywhere from weeks to months just on that step. You're going to do a computational process. You're going to synthesize molecules. You're going to run the testing regime, and then have to analyze the results. Just doing that computational process with classical approaches today, we'll spend days to weeks, potentially a month, just running the computation. Then you're going to go to a second iteration, third, fourth, each time optimizing a different property in a sequential manner. Polaris changes this paradigm by using the quantum annealer to instead express multiple properties concurrently in the QUBO and optimize them in a single step. We're only utilizing on the order of a second to a few seconds of QPU time, and we're able to look at billions of molecules, in contrast to the current industry process, which is looking at thousands of molecules, and on the order of weeks of time just to do the computation. So this is a significant savings in terms of time and allows us to look at an incredibly larger combinatorial chemical space than current industry processes. So this is a visualization of the process I'm describing to you. Shown in blue is a protein. Highlighted in gray is a binding pocket. That's where a small molecule needs to sit to change the functionality of a protein. This will change the disease process. You might think about breast cancer, BRCA, or HERG mutation. By interfering with the protein, we're now interfering with the disease process. That gray binding region is how we know what chemistry to actually insert in there, what sort of chemical components are going to create drug molecules. We work with both de novos, so novel synthesis, as well as on-demand fragment libraries so that you can accelerate the process not only from the computational perspective, but also by streamlining the process to get molecules delivered in a rapid manner on the order of 2 weeks to 2 months. So once we have described the chemical space we want to search, we express that as a QUBO and can optimize over a variety of properties. Some illustrated for this project were bioavailability, synthesizability, and fitment in the binding pocket. The output is a library of on the order of 3,000 molecules. This library will be fed into traditional CAD, computer-aided drug discovery pipelines. that are used for the downstream process. So, why quantum and why now? We're able to greatly accelerate the process. We're compressing time from a discovery process that is years down to a matter of weeks. We're able to achieve significant cost savings. Again, instead of spending 3 years and $4 million, we're compressing that down significantly. Looking at such a large chemical space compared to traditional methods. And finally, we're able to have a much faster iteration cycle with medicinal chemists. So when they look at the results, we can simply go back and reformulate the QUBO to optimize other parameters to get different scaffolds. For us, this represents quantum utility. We're extracting valuable, actionable results, decreasing our cost and time, and delivering value for our customers. With that, I'll pass off to Maurice.
All right, thanks, Bill. So my name is Maurice Benson, and I'm going to take a minute and we're going to talk a bit about the science behind what we do, how we actually map that science to the quantum annealer, and then, as Bill said, some of the quantum utility we're getting from using D-Wave's advantage. So we'll start off by this is a protein, kind of like, again, what Bill said, it's controlling some biological process. And if we look at that, we have a small molecule that we're fitting into that protein. Now, for this depiction, we're actually going to look at the polarity of that space, so we can kind of start to see we have our polar and nonpolar areas. That's how that small molecule fits into that protein. And then finally, we have this 3D surface of the pocket, and that's essentially what we're trying to do, is trying to find different molecules that will fit into that 3D surface, but also stick to those polar and nonpolar areas. And how do we do this? We leverage a technique called fragment-based drug design, where we can take a small molecule, as you can see here in this image, and break it up into pieces. Now, this is one way that we can fragment this molecule. There can be multiple ways to do it, but for the sake of this conversation, we're going to talk about this one. And as you can see, we have 4 separate regions we can break this molecule into. So we've broken that molecule into 4 different regions. Now we can think of those different pieces as like our references. So we can go into our database and find other molecules that look just like that reference and form what we call a fragment library. Now, using that fragment library, we can go through and try to make a bunch of different combinations of those different fragments that we picked that have the same physiochemical characteristics of that binding pocket for that protein. And then finally, we can use the quantum annealer that will spit out other molecules that share the same, that satisfy the constraints that we've had, and have the same physiochemical characteristics. So what we've done is we've turned this into a constraint satisfaction problem, and if we can see here on the right-hand side of the screen that we've mapped brute forced a very small fragment library, and you can see that first, there's a lot more of those gray dots. Those are molecules that we could potentially create that aren't synthesizable. That way, if we try to send them to the lab, they physically could not create those molecules. So you can see there's a lot more of those. And then we have that lighter green that you can see that those are molecules that are synthesizable, but we're actually only looking for the molecules in blue. So that's the ones that have the very high pharmacophore score or map to that physiochemical characteristics. So on an average, we're only looking at about 5% of that whole combinatorial space. And it's just very difficult to narrow down that space with a classical computer. And just for kicks and giggles, we usually have fragment libraries that are about 10 times larger than what's depicted here. So it's quite difficult. You can see there's quite a few combinations. So how do we get to that, those 5% that we're actually interested in? Well, we leverage D-Wave's binary quadratic model. So we're going to take a beat and we're going to step through some of the math on how we can map our constraints from this chemical space to this equation. We'll start with looking at the bottom. We can think of that V sub I. Those are the individual fragments in our system. And they have to be either 0 or 1. I like to think of those as choices. Either that fragment was chosen for the molecule or it was not chosen for the molecule. Just a kind of an easy way to kind of keep it in your head. So for this piece, we can think of A sub I and V sub I as the penalty or incentive for choosing that molecule or for choosing that fragment. So we might have some fragments that are better than others, some fragments that have different properties, and we could think of that A sub I as that penalty or incentive. And then on this side, we have that B sub I sub j, V sub I, V sub j. And we can think of is the B sub I sub j as that is our penalty or incentive for choosing the combination of those two fragments. So we have some fragments that might play really well together. They actually combine and have good physiochemical characteristics. We have other fragments that might not, but we can use that B sub I to penalize or incentivize that. And then essentially we're trying to minimize this equation. What I'm going to do is we're going to talk about one of the constraints we use, the one hot constraint, that we're going to make sure that only have one fragment per section. Right, so we can see here we have 4 sections. We think of one of those. It doesn't make any sense to put 2 fragments into one section. So we want to make sure that the molecules that we get back only have 1 fragment per each piece. So we're going to have a little thought experiment, and we can pretend that we have a molecule that has 3 regions, and each region has 3 fragments per region. So we can look at this R1, and we have, that is region number 1. And then we have V1, V2, and V3. We can think of those as 3 fragments that would fit into region 1. We're only going to talk about region 1 for this conversation, but essentially it extends to region 2 and 3 also. So we have this one hot constraint. So with a little bit of math, we can think of a V1 plus V2 plus V3 has to equal 1. So it's just kind of a way to represent mathematically that we only want 1 fragment per each space. And then we can turn that into a one hot penalty. By moving that 1 to the left-hand side of the equation and squaring it, turning it into a quadratic function. And that's going to allow us to, once we expand that function, we can start to see that we have both pairings and individual values, both linear and quadratic values, that can represent our problem. So we can dig into those right there. So we have V1 and V2 with a coefficient of 2. So we can think of that as if you choose V1 and you choose V2, you're going to be penalized by 2. So again, we're trying to minimize that function, so adding a positive value would be a penalty for that. But on the other side, we have this linear term where we could think of that as a -1 times V1. So if we only choose V1 for our system, we get a -1 incentive. And that allows us to map this to a matrix. We could think of our linear terms as being on the diagonal, and then our quadratic terms are on the right-hand side. So now you can see that if we choose just one of our terms, we get those -1 values, and then if we choose 2 or more, that we get those positive values that penalize that system. And then D-Wave's Ocean platforms allows us to easily map this matrix and send it back to the D-Wave Advantage to solve the problem for us. So why do we choose the binary quadratic model? So building this model allows us to customize the constraints. I've talked about an equality constraint today. We have V1, V2, V3 equals 1, but you can also do inequality constraints. So we might have a property like listed here as hydrogen bond donor, and we might want that to be within a certain bound. So this model allows us to express that constraint. And then we can also manage the penalties and incentives for these constraints. So like we said before, the one hot constraint is very important. I only need 1 fragment per each region. So that might have a really high penalty, but maybe I can get by with the HBD being a little out of the bounds, so I might lower that penalty. Right now, we can represent about 100 fragments per run. That allows us to build quite a few combinations. And we can run about 3,000 reads per run. So that essentially we could potentially get 3,000 molecules back that fit our constraints. We don't always get that many back. Sometimes we get duplicates. So we always get at least quite a few. And then the nice thing about this is compared to all the other techniques, it only takes less than a second to run. So now we can talk about some of the utility that we're getting out of the D-Wave Advantage. And this starts to talk about the fitness of the solutions that we find. So when we compared, we did a case study where we did a case study using the JAK2 protein, and we wanted to see if we could find small molecules that would interfere with that protein. And we compared the D-wave annealing to classical greedy search. And what we found is that we ran each 100 times, but we only allowed each system to run for 5 seconds. So we kind of tried to put them on the same plane. And what we found is even though given the same amount of time, that D-Wave's annealer constantly gave us molecules that had a higher pharmacophore scores. That's just saying that the molecules that are coming back fit our constraints better, but also fit that optimization or that objective function better too. But what's really exciting also is that the D-Wave annealer gave us more diverse solutions back. So when given both, they both had 100 fragments to play with. The D-Wave annealer used 50 more fragments than the classical greedy search. So that diversity of solutions allows us to explore a wider chemical space. And with that, I'll pass it back to Bill Shipman to talk about some of our case studies.
Very good. Thank you very much, Maurice. So for the first case study we're looking at, this is for a protein. It's an oncology protein, NNMT. We're looking at a reference molecule in green on the, I guess, left-hand side. Sorry, I'm not very good with my left and right. But so we have the template molecule highlighted in green. We see a quad molecule highlighted in red. That molecule is emblematic of the set of molecules that will come out. We can see that it occupies a very similar physical shape within the binding pocket. The binding pocket is that yellow sort of ribbon behind the molecule of interest. And if we actually zoom in a little bit, we'll see that on the red quad-produced molecule, the fused ring system in the lower left, highlighted in the red circle, has both shifted orientation and the actual fragment has changed. I'm not a chemist. I cannot tell you exactly what that change means, but I can tell you our chemists and our customers are very interested in that kind of change. It may affect the synthesizability or solubility of the molecule, but that is emblematic of the results we see in an individual way. If we look at the quad-produced molecules in a larger context, we can compare them to decoys. That's a canonical way of comparing molecules in computational chemistry. These decoys would have the same or appropriate physical and chemical signals, but are not active. They are not valid binders. We can see the quad molecules are significantly differentiated and have better docking scores. The quad molecules are highlighted in red. The second graph on the right-hand side is comparing quad molecules that took roughly 2 days to process and then analyze, compared to chemist-designed molecules that took roughly 2 months. So this is a rehash of work we did. The chemists originally worked on this project at nearly the inception of Polaris, so almost 4 years ago. And with the production of quad, we reran the same project to see what the performance difference was. So we can see that quad produces significantly better docking scores for the molecules compared to the molecules that chemists designed in green. For context, we have control molecules highlighted in blue. Those are drawn from Kimball and are known inhibitors for NNMT. So we can see that quad is producing molecules that are better than manually designed chemist molecules, as well as outperform control reference known inhibitors. Maurice talked a bit about some of the properties we optimized. So from this case study, here are 2 different properties that were optimized, TPSA and number of rotatable bonds. That again is 2 primary features for describing drug-like molecules. You can see that the quad-produced molecules in red for TPSA have a much narrow band of values compared to other known inhibitors from Kimball. Likewise, number of rotatable bonds, the quad-produced molecules are in a much narrow band of values which are appropriate for drug-like molecules. From this case study, we can see that quad is producing molecules that fit within the binding pocket, outperform decoys, known inactive molecules, and outperform molecules designed by hand by computational chemists and have drug-like properties. If we look at a second case study, this is using a specific mode in quad, best in class. That's for taking a reference molecule, in this case sorafenib, which is a oncology medication, and how it fits within the p38 MAP kinase protein. So for best in class, we're taking sorafenib and looking at the adjacent chemical space to find superior, best in class with regard to the reference. So on the left-hand side, we see sorafenib, p38 MAP kinase depicted in blue with sorafenib placed in three-dimensional space in sort of a banana shape, shall we say. The left-hand side, we see sorafenib as a 2D planar structure with multiple bonds highlighted. That is where we can fragment. This is a view of the interface that the chemist would use to fragment the molecule into the regions that Maurice was describing. These highlighted bonds allow chemists to either choose very small fragments or perhaps larger fragments to maintain structural motifs as the project dictates. So, looking at their set of results that came out of Quad for this best-in-class work, we found novel molecules, but we also found prior art in the form of patents and other molecules described in literature as inhibitors for p38 MAP kinase. We can reasonably infer from that we are finding not only novel chemistry, but chemistry that is appropriate to inhibit p38 MAP kinase because the data set itself intrinsically has other known inhibitors. How can you use this in practice? You might use it to create a better IP moat when you file patents for a novel compound. You might use it for a fast follower. There's an initial patent disclosure for a novel bit of chemistry. You might explore that and look for adjacencies. Those are two ways. There's a lot of other ways that I think we can all imagine how you could leverage this tool. So finally, if we look at the final part of this case study is to look at a heat map with the results clustered. So this is roughly 3,300 compounds that were clustered based on max keys. That's a fingerprinting function and identity function. And if we look at the area that's highlighted, that is emblematic of what you would see if you actually visualize the molecules in that red box. You'll see they all exhibit a very similar structural motif. There's some variation, which is what we want. This is what we saw in the very first case study with the difference of the fused ring system. So this is a second case study. What are our key takeaways? Using D-Wave's BQM solver enables Polaris to solve an incredibly large chemical space that is infeasible with current industry approaches. We're producing results that are relevant for our customers and leading to repeat customers. For any organization, repeat customers are a hallmark of success. In biotech, it is even more so because that means that we've gotten to wetware, physical chemistry, and produced valid results that are worthwhile. Finally, quantum utility is available today. Please don't get lost in the definitions. Go with technology that drives measurable outcomes. Thanks so much. Have a wonderful day.